There. Pointer options. There we go. Okay. So last time we were also talking about relativity, and I want to get rid of myself here. There we go. Um, and lots of times people say, well, yeah, but what does this mean to me? It means nothing. Um, it's fun to talk about, but if it doesn't have any real life applications, what's the big deal? Well, everybody has their phone, and there's GPS in your phone. And the GPS satellites are affected by both special and general relativity, so the speed of light and gravitation. Special relativity predicts that atomic clocks moving at the GPS orbital speeds will tick more slowly than stationary clocks on the ground, with a delay of about 7 microseconds, so 7 millionths of a second per day.
Okay, well,
And this time dilation effect has been measured and verified. They're also affected by general relativity in that a clock closer to a massive object, so a clock sitting on Earth, will be slower than a clock farther away from that gravitational influence. And this causes the GPS clocks to be faster by about 50 microseconds per day. If these little tiny bits were not compensated or corrected, you would get an error of roughly 10 kilometers a day on your GPS, which means they would be totally useless. So this is just a graph kind of showing you how general relativity and special relativity can be compared to the Earth. So here we just have different times offsets. On the x-axis is the kilometers from the Earth's center. So here we are right at the Earth's center. Here we have Earth's surface right there. And that a line right beside it is where the shuttle or where the International Space Station orbits. So not really affected much, but just a little tiny bit. The farther we get away from the gravitation of the Earth, we can see that this green line shows us the farther we get away, the faster the clocks would run. But it's also, as we get farther away from Earth, the GPS orbits um, are much faster than if you were standing on Earth, and that gives an orbital speed slowdown. So the faster you go compared to with Earth, the slower their clocks will appear. So at GPS orbits right around here, right about 27,000 kilometers from the center of the Earth, you have to combine the slowdown with the speed up, and that gives you your net orbital time. And the engineers who send these things up actually have to offset the satellites just a bit, so they will be in sync with the ones on Earth, and all your GPSs will work well. We also talked a little bit of gravity and how this is the general way people think of gravity. Um, my problem is that it only shows 2 dimensions, but you can see, so this grid work is space-time, and you have a mass that actually warps the space-time. I prefer to think of it three-dimensionally. So these grids are three-dimensional space-time, and here we have a mass, and you can see actually space-time is warped towards the masses. So kind of in here, you think of the mass warping space-time away from it, but here we can see it's actually being warped toward the mass. And one of the ways I really like thinking about gravity is using contour maps like this. So we have two objects. In this case, there's the sun and the Earth. And we can see these contour lines that gradually get wider as it gets farther away from Earth. So that's the different degrees of gravitational force that's being applied, and which is nice and smooth when you only have one object. If you have two objects, their gravitational fields interact with each other. And it turns out that there are 5 places where the interacting gravitational forces actually kind of cancel each other out. These are called the Lagrange points. Like say there's 5 of them. L1 between the Earth and the Sun, L2 on the opposite side of the Earth. These ones are about 1.5 million kilometers away from the Earth. Another point, L3, is directly opposite the Sun. And then we have L4 and L5. These ones are kind of interesting when you talk about Jupiter. So if this was Jupiter, turns out that at L4 and at L5, there's a whole bunch of asteroids. So it's a gravitational null field. As Jupiter goes around, that field or those 2 areas go around too. And it just kind of collects the asteroids in a place where nothing is pulling more than anything else. For L2, that's becoming a really popular place to send satellites and telescopes, and the James Webb Space Telescope will be sent there. Hopefully it's going to blast off in October of next year. Already there's several probes there. It's also a good place to park satellites that are of no use anymore. No real fuel is needed to keep them at this point, so it's very economical to use. So on to time travel. So in 1895, H.G. Wells wrote a novel called The Time Machine, and that really popularized the concept of time travel by mechanical means. And we've seen this in Back to the Future series, the DeLorean and the Dr. Who TARDIS. Now, 1895, that was before Einstein wrote out his special and general relativity. So this purely fictional idea of time travel. So is it possible to travel through time? So within a human lifespan, is it possible to travel into the distant future? And is it possible to travel into the past? So our current understanding of fundamental physics tells us that the first answer is a definite yes. We definitely can travel into the future. And traveling into the past, well, maybe, but probably not. For traveling into the distant future, we can use that time dilation effect of special relativity, which again states a moving clock appears to tick more slowly the closer it approaches the speed of light. And this effect applies to all types of clock, including biological aging. So our biological clocks would move slower also as we get closer to the speed of light. If you could leave the Earth in, say, a spacecraft that could accelerate continuously at a comfortable 1g, so that's the force that we feel on Earth, 1g, equal to the gravity at Earth's surface, that was a continual acceleration, you would begin to approach the speed of light relative to Earth in about 1 year, just under 1 year. If you could keep on accelerating, you would even get closer and closer to the speed of light, and the clocks would appear to run at an ever slower rate, again, relative to Earth. Who's ever in that spacecraft experiences time quite normally. So a round trip to the center of our galaxy and back to the Earth, it's about a round number of 60,000 light years there and back. But if you were in that ship, that spaceship, you would only have spent 40 years of ship time. And upon arriving back at Earth, while you're only 40 years older, the Earth would have gone through 60,000 years, would have passed on the Earth. So that's definitely traveling into the future. There are certainly a lot of engineering problems, not the least of which is being the amount of energy required to do this. Now remember, energy is equal to mass times the speed of light squared. So even if there was a perfect conversion of mass into energy, you would need a planetary size mass. So about the whole Earth mass completely converted into energy to do this trip. But there is nothing in the laws of physics that would prevent this trip from occurring. So physically, and specifically physics, it's possible, but there certainly are some limitation factors there. This 100% efficiency. So in the core of every star, hydrogen is being fused into helium and giving off heat and light. That is only 0.7% efficient, and that's the most efficient we know of. So getting anything we can do for 100% efficiency certainly is an engineering problem that has not even been attempted yet. And how do we kind of know this? Well, the world's particle accelerators do this every day. So here we have the Large Hadron Collider. It's a 27-mile tunnel under these cities. That's just, so it's just being overlaid here to show you where it's at. But it's under these cities, and they can boost hydrogen to almost the speed of light. 99.12345 and then a 1%. And particles going that fast decay more slowly than those at rest. So that's that special relativity. You go fast, you go slow, or your clock goes slow. And they've measured this to a very high precision. So this is happening every day. The astronauts, if you want to bring it a little bit back to a practical, the astronauts aboard the ISS, they are going, so they're above the Earth, so they have less gravity, they're going faster than the Earth, so that special relativity kicks in. They actually return to Earth 7 1,000ths of a second younger for every 6 months they stay at the space station. So they are going into the future by 7 1,000ths of a second. If you talk time travel, everybody thinks of wormholes.
Colleen, I got a question about the
Sure.
Hadron Collider.
Yep.
I know that they're looking at making a bigger one in China.
Yes.
And why? So would that be to get it to further to get it faster, or what would be the purpose of making a bigger one? Would you say 27 kilometers underground, using huge magnets, right?
Yes.
Cool
Yes.
magnets.
Extremely powerful magnets. When those magnets turn on, it uses more power than all the little cities around it combined. So yeah, it's just the bigger you can get it, the faster you can make them go. And even though this is, really, really close, there possibly are particles or things they can learn by getting closer and closer to see.
Right.
So they spin these things around really fast. They have one stream going one way, one stream going the other, and then they collide them together.
Yeah.
Which you can think of as the energies are so high, it actually kind of melts them, or at least breaks them down into possibly what was available at the Big Bang. And then as they cool or spread out, move out, they can see these other particles. They found the Higgs particle, which is something that imparts mass to other particles a couple years ago at the Hadron, this LHC, because they could get up to those high energies, those fast speeds.
Wow.
Yeah, I know. So wormholes. These are hypothetically warped space-time, and they are permitted in general relativity. But right now, any theories of them are just on the quantum level. So just, proton and nucleon or neutron sized particle wormholes. They actually may be 1/1000th of a centimeter across. So very, very tiny. They are not stable and they disappear in a small fraction of a second, but nobody has actually seen one yet. This is all the hypothesis and the experiments they're trying to make a theory out of. So if you were going to use one as a time machine, you would need to make a traversable one. So one that's big enough for a human or a spacecraft to go into it. Again, two ways. The first way is you would take one of the ends of the wormhole and you would accelerate it to a significant fraction of c, speed of light, and then bring it back to its origin. So there again, we're talking special relativity, using speed to go ahead in time. The other way is using the gravitational field or general relativity of an object that is much heavier than the area around the wormhole. So you'd take one end of the wormhole and ship it off to something very massive and then bring it back. So you're using the gravitational delays there. Both of these methods would then cause that time dilation. So one end of the wormhole would have aged less than the other end. And this means that if you entered the younger end and exited the older end, you would actually be in a time, and then went back, you would actually have gone back in time. Don't get me to explain that. You know, general relativity is like a PhD all on its own. One significant limitation of this time machine is that it's only possible to go as far back in time as the initial creation of the machine. So you can't go further back because nothing had been created at that point. According to the current theories on the nature of wormholes, construction would require the existence of a substance with negative energy, often referred to as exotic matter. We certainly have no evidence that negative energy or negative masses exist. And there has never been a naturally occurring wormhole observed. So we don't even, they look good in the math, but we don't know if it's actually physically possible.
So the idea of wormholes and this whole like time travel, like,
yep.
Is this a science fiction idea that people are trying to prove by using science, or is the wormhole a science term for the idea for this phenomenon or this?
Wormholes are certainly popular in science fiction because it's been said that it is one way to go back and forward in time and to go travel great distances quickly. And that's the one thing now. Remember when I was showing those 3 dimensions of gravity? So wormholes are always, or not always, are often presented with this warping of space-time, and this kind of funnel that goes down, which has led people to think that, well, maybe somewhere else in the universe, there could be an exit with this warping going up, and these two things can be combined. Mm-hmm. So everybody, oh, okay, that seems, but if you look at it 3-dimensionally, and I've never heard anybody talk about this. Nobody ever explains this bending of the universe. I don't know if this is just a convention to use to, just show that these things could be very, very far apart in the universe, or if there's actually any theories or hypotheses about what you would have to do to hook up to wormholes. And I think it's that 2-dimensional figuring where you have that space-time going down. And for a black hole, of course, it just keeps going down. There is no end. And it's that, people mind thinking of, well, you could join up 2 of those, where it's actually not. Remember, space-time isn't being warped away from the object, it's being warped towards the object. So right. For me, a black hole is a single thing within 3-dimensional space-time. It can't go anywhere else. But, I could be wrong. Who knows, right? Speaking of black holes, so black holes are so massive that, of course, they warp space-time just like general relativity says. So time passes more slowly for those who are near a black hole. Scientists estimate that individuals could feasibly get close enough so that time could be cut in half. So if you spent 5 years going around a black hole, 10 years would have passed in the rest of the universe. And it's been thought, well, you know, maybe you have some disease that science is just about on the edge of solving. So put yourself around the black hole, you know, you would age slower when you came back, maybe there'd be a cure. So if you spent 5 years going around the black hole, 10 years for the rest of the universe. However, this may work, but the closest known black hole to us is 1,100 light years away. So first you got to get to the black hole, then you got to go around it, then you got to get back to Earth. So it may not be good for disease cures. This is a graphic just showing how space and time is warped around a black hole. So we have the black hole in the center there that would have an accretion disk around it. This is stars and material that are swirling very, very quickly. And when we see it on edge, we'd actually be able to see the back part of the accretion disk. We'd see some above it and some below it. So if we could see a black hole from different angles, that's kind of what we would see. One other thought about time travel is a Tipler cylinder, also using general relativity. So if a cylinder is infinitely long and spins fast enough about its long axis, then a spacecraft flying around the cylinder in a spiral path could travel back in time, or maybe even forward, depending on the direction of the spiral you go. However, the density and speeds required is so great that, of course, ordinary matter is not strong enough to construct it. So we know of nothing that you could use to make this infinitely long, fast, quickly spinning cylinder. A finite cylinder might be able to be used if the rotation rates were fast enough. To make this work, you would need matter that is roughly 10 times the sun's mass. So you need a lot of matter. Then you would need to roll all this matter into a very long and very dense cylinder.
So a little bit of a neutron star, right?
Yeah, you probably even more dense than that. It would be a bit like squishing a black hole through a spaghetti factory. So you have the density and mass of the black hole being extruded into this long cylinder. The key to this device is its spin, which needs to be a few billion revolutions a minute. So I'm not exactly sure how you could manage that. And certainly that would take some very good material engineering to be able to do that. And so what if you manage to get that cylinder and get it rotating fast enough, a spacecraft following, now this is also a problem, a very precise spiral around the cylinder could possibly travel billions of years into the past. However, Stephen Hawking has proved that time travel would not work with a finite cylinder. It would be only possible if the cylinder is infinitely long. I'm not sure how you make anything infinitely long. Along the same kind of lines, we have the Alcubierre drive. So Miguel Alcubierre came up with this idea based on general relativity. And it is a machine that would change the geometry of space by creating a wave that causes the fabric of space-time ahead of the wave to contract and behind it to expand. And then the spacecraft would then ride inside the wave in a region of flat space, so no expansion, no contraction, called a warp bubble. When Star Trek started using the term warp speed, they just picked a thing out of air. There was nothing connected with anything real at that time. And if you're inside the bubble, you would not be moving around, but that region would be moving through space-time. And if, again, there's this, if you could have a negative mass created, you could actually go faster than light, which some scientists think if you go faster than light, you are automatically traveling backwards in time. To build this, the energy equivalent of 10 to the 64 kilograms would be required to transport a small spacecraft across the Milky Way. And that is many times greater than the estimated mass in our whole observable universe. So not very good gas mileage. Something like this is we see every day in the expansion of the universe. So there are galaxies moving away from us right now that are going faster than the speed of light, but they're not moving through space. It's space between the galaxies that is expanding. And if you have expanding space between all galaxies, the farther you look away, the faster everything seems to be going. And indeed, there are probably lots and lots of galaxies that have passed the point where we would ever be able to see them, because they're now going faster than shouldn't say they are going, their space is moving faster away than the speed of light from us. One final possible space travel is to use cosmic strings. Some scientists believe that these string-like structures formed in the universe right after the Big Bang, and they're spread throughout the whole universe, and each individual strings could be millions of light years long. Now, again, they're thinner than an atom, and for some reason that I couldn't find out, they have extremely high gravitational force.
So are these something that's known to science, or are these hypothesized?
These are hypothesized, yes. So we have this thinner than an atom, millions of light years long. And if two got close together and were parallel, the math shows that the gravitational force would be able to distort space-time that might be used for time travel, possibly both forward and backwards. Again, none of these are known to exist, and it does not seem possible to create new ones. That doesn't mean we can't think about it. And one last thing I'd like to leave you with is one of the newest pictures of our Milky Way galaxy. This is looking towards the center. And in this little tiny picture, there are 10 million stars. It is about 4 by 2 degrees in size on the sky. So if you put your thumb out, that's how big an area of the sky that this is covering. There's a bigger one. This is actually just a small fraction of the whole one that they've created, which is 10 by 20 degrees. So 10 degrees is your distance of your fist. So it would be 10 by 20 degrees on the sky. So that much, and it contains 250 million stars. And what I wanted to do is just, nope, not that one. I can't seem to find it. It's zoomable. I need to do. No, no, no. I need to go here and then go there. Okay. So here's that same picture, just a small part, but you can actually zoom in on it. And you can just see more and more and more stars.
Oh, we can't see it.
Oh, really? Oh,
Uh,
okay. Well, let's just try. Okay, let's try. Screen share. Now?
it's coming. It says it started to share screen. There it is. Yeah.
Okay, so here's that picture. And you can keep on zooming in and you just see more and more and more stars.
Is that a off a website or an app or?
Yeah, I will give you the link.
Wow. Look
So
at that.
these big stars, those are stars that are closer to us. The black stuff is that cold hydrogen and dust ready to form new stars. The glow is from the 10 million stars. And this one I think is pretty cool. So here we have a brand new star cluster. These stars are probably maybe 1 billion years old, so just maybe not even that old. There are a bit of color change, so there are stars evolving. But this area probably started like this area at one point. So huge clouds of cold hydrogen and dust. There are probably stars forming right inside this area here. So thick you can't even see stars on the other side. So this is where stars are born, in these big clouds. Oops, there we go. And I will there's the link for that.
Okay, great. I'll add that to our site.
Here.
Cool.
So time travel into the future, absolutely positive. But once you get there, you can't get back.
Right. So you can't even go, you can't even tell everyone. Yeah, it's not.
I mean, you could tell your great grandchildren that time travel exists, but by that time it's probably already come out.
You weren't even know who they are. How would you find them?
You wouldn't know who they are. DNA. To find.
What year were you born? 2000?
Yeah.
That's assuming the Earth is still here, you know, and it has breathable air and you can land on it and things like that.
Yeah, that would be the worst, just to get back and the Earth's not even there.
Yeah.
Do you have time for us to go around and just share how you blew our mind today?
Absolutely. And any questions you might have, absolutely.
Yeah, sure. So gang, you ready for share? Okay, we'll start over here with Anna's over there. We'll come back to her.
You know, during this entire time while you were having a presentation, I was thinking of something that I mentioned earlier to the rest of the class, a quote by Carl Sagan. It was talking about how science is not a collection of knowledge. Science is a way of thinking, so that we can meticulously, meticulously interrogate our universe. So this was just being able to see all these little things and people may not realize is part of this sort of area of science. It's space and these sort of theoretical these theories and all that we have that don't get past theories.
Yeah, yeah, a lot of hypotheses don't get past. I had a point. No, can't think of it. I'm getting too old to remember things.
But yeah,
Oh, yes, my point. Science literacy is so important with all this media, social media, and fake news. And you need to be able to be at least be familiar with some of the concepts so that you can look at stories and kind of see if they're heading in the right direction or they're trying to lead you off some bad path.
Neil deGrasse Tyson, he said, knowing how to think will empower you far more than people who know what to think.
Exactly.
Austin?
Just even stuff like stars and galaxies lends light, not just black holes. So stuff like
What,
that.
just like the gravity of those bend light?
Yeah.
Yeah.
Yeah, gravitational lensing. It's become a great tool. It acts like a telescope, so we can see things even farther and farther away or farther and farther back in time.
Cool.
Kind of interesting that it would be possible to time travel. It wouldn't really help you in any way.
Yeah. That is possible to time travel, but it really wouldn't help you in any way.
Oh, that's right.
Newman?
Yeah, time travel, it's really cool. It's good. Yeah, it's really good. It's kind of not a whole lot of it. It's like, I kind of figured that it's like, you might, forward would be a thing, but back not so much. But it's just like, yeah, okay. That's cool. You going forward in time, your galaxy is back to nothingness, and you're stuck there now. Have fun.
I'm always thinking too, I'll say going to the past was kind of possible, and I wanted to go to yesterday. Do I go to the place in space where Earth was yesterday? And is Earth going to be there for me? I've never heard anybody, say, oh, don't worry, you're still going to be on Earth.
Yeah.
Or maybe in the middle of Earth.
Because Earth is traveling along so quick, right? So if you,
Exactly, yes.
whoa. Cam?
It's really cool how big the universe is, or the Milky Way, like that last picture you were showing us, this picture of the Milky Way. And you said that there was a very big number of stars, and you kept zooming in, and it just kept looking exactly the same. Because
Yeah.
I don't know if that makes sense, but it's really big, and it's weird to think that we're just these tiny little things.
In the grand scheme of things, yes, we are tiny, but we're amazing.
Bill? Or sorry, Will, sorry.
Will or Gil? I'm just gonna say time travel is crazy. It's such a weird concept to think of, just like that you could physically time travel. You could actually go to somewhere, but there probably might be a way to get back, but it's just trying to think of exactly. There's actually no way to get back.
Yeah, the math doesn't show any way to get back.
Bill?
Well, I like the time travel because that'd mean that I'd be able to know what kind of car I could have in the future.
Yeah, but then you're stuck there.
Yeah, I wouldn't be able to brag about it to my friends, so
No, you
I don't
just
know if that's a
never
good
did.
thing or a bad thing. Bring all your friends with you to brag about it.
Yeah.
Conrad? The back there?
I just like the time traveling.
Yeah, like the time travel, how about you, Jared?
I thought it was kind of weird that somebody could think of an infinite cylinder for time.
Yeah,
I find that really weird that somebody thought of that. And I'm just
well, again, it comes from the math, and that Stephen Hawking, showed that an infinite cylinder is fine, but a finite cylinder is not. So that kind of shows me that that's not going to happen.
Mm-hmm.
and the thing about going out like 40 years
with stuff and then coming back like 60,000 later. I thought that was cool.
Right. Going to the center of the galaxy, is that what it was? Around the black hole and coming back?
And remember, so real space travel, if you were heading to the center of our galaxy and wanted to come back, you only accelerate for half the time. Then you have to flip your ship over and you have to decelerate so you can stop. And then do the same thing on the way back. Accelerate coming halfway back, then turn around and slow down.
Oh yeah, I guess you're not going to want to be flying by Earth. Yeah.
You want to
No, at light speed, no.
Wait,
Riley?
I'm kind of lost on what's real and not real.
You hear that? He says, I'm kind of lost on what's real and what's not real.
Yes, I think every astronomer, every scientist comes to that point. Comes to that conclusion at one point. All in the math, though.
Yeah, I found it super cool looking at space and seeing and using those like the gravitational lines as like ISO lines or
Yes.
right. And then just looking at the areas where you can put things where it's not really being as affected by gravity in other places. You know, you kind of tend to think of, you know, space as being just this vast emptiness, which the majority of it is, but there's all these other places with, you know, that are being affected by things that are around them.
Yeah. Gravity is the weakest force, but it reaches out the farthest.
Cool. Any questions, gang? Oh, you got a question, Bill?
yeah. So if you were to go towards the center of the Earth or the center of the universe, and then turn around, come back, and instead of just stopping at the Earth, go back past the Earth, wouldn't that reverse the whole effect of things? Like, wouldn't you go back in time?
Nice thought. If you're still traveling at relativistic speeds, if you're still traveling at time, you know, at speed of sound, light, your clock is still slow. So it's not until you get back to Earth, like you actually stop, that you can tell how what distance you've traveled or what time distance you've traveled. So that thing about the black hole too, going to a black hole, if you were in a spaceship parked away from a black hole and one astronaut got out and went towards the black hole, you would see him slowing down more and more. And right at the event horizon, that's where you would see that astronaut frozen in space. You would not see him go into the black. Of course, for him, he's going in, or she. But from, again, the relativistic views, with general relativity, you would see him actually stop at the event horizon. I know.
Oh. Huh. So you would never see them go in?
Nope.
No.
How does that make any sense? It does because science.
Yeah, he's like, how does that make sense? Ah!
It's in the math. It's in the math.
We got minds exploding.
I've done my job.
Again, success again. I didn't think you could top weird things in the universe.
Yeah, that was pretty weird.
Yeah.
So how about next week?
Okay, any ideas for next week?
I do have some little bit of put together some of the record holders, like the biggest star and the smallest star, and
Oh, that would be cool. And actually, I'll have to get back to you. I'm not too sure if we're here next week, if we have the space class, but I'll send you a message.
okay, sure,
After school today.
okay,
Yeah, but that sounds interesting. The biggest star,
yeah, all the record holders.
Roy, follow the cookies.
Oh, that was another one. Someone just said to completely destroy Hollywood movies.
Plot is good, no problem.
Someone was mentioning they think that that would be a cool thing at the Science Center would be taking Star Wars and all the things that are wrong with the science.
That's what I.
Yeah, that was Jake also suggested that one. Yeah, that would be cool.
Give enough room for that.
Yeah,
There's so much stuff wrong.
yeah. But that would be interesting. Maybe I'll get to, that can be a project he does.
Yeah, yeah.
Right, maybe we can get a little space, a little area up in the Science Center, put on a display.
Yeah, I've started on the little solar system display, and we're getting some infographics made up now for it. So
Oh, it's starting to come along.
yeah, it is. Yes.
Oh, good. Good.
Okay, well, I'll be ready for next week.
Yeah, and I'll let you know as soon as I can here.
If not next week, then the week after.
Sounds great. Thank you very much, Colleen. That was awesome.
Thank you very much again. I really want to thank you for inviting me to do this, because I'm learning so much too. And it's solidifying some of my thoughts too. So the best way to learn is to teach. So thank you.
Oh, no, thank you. No, this is awesome.
Okay,
Next week or the week after.
sure thing. Bye, everyone.
Wiedersehen.
Thank you.
What did you say?
Welcome.
Oh, I got to make sure I get the.
It's still recording.